So guys, let's get started. As I said before, logs is a lifeblood of our system. They can record everything, what just we want. It can be good thing, bad thing, routine and unusual, as loggers has different levels like warning, error, and stuff. But when you're running a modern platform, you generate not just hundreds, but millions of log entries every single day. So we gotta separate the valuable signals like emerging outage or a security incident from all the background noise. That's where embedded context agents really come in. The challenge of logs. Think about the scale of the problem. In a microservices-based architecture, each service produces logs. Multiply that by dozens of services, multiple environment. It can be like staging, production, QA. As well, we have different countries. They locate in different regions, like Europe, Asia, and US. And as I said before, since we use microservices, their amount can be like thousands at least. For example, when it comes to fine company, like as I know, Netflix has 700 at least. Just let's imagine how many of them has Google. So most of those logs are boring. Things like, for an example, connection open or user disconnected or some WebSocket is open and stuff. User logged in, cache hit and stuff. It can be a lot. But hidden on those streams are the needles and the hashtag. The early signs of something going wrong. Maybe just request is timing more than usual. Maybe login failures are increasing for a specific country. Probably some database shard is slower than the rest. It's not really something important, but when we have huge amount of them, it's getting the problem. So we got to recognize when it's okay, and when finding them is a noise is a real challenge. And why is it's really hard? Log analysis is hard for three reasons. As I said before, we have huge volume. You cannot have humans reading through millions of entries. Even automated dashboards can be overwhelming. And heterogeneity. Just let's imagine it's really frequent situation when one team is using some strict structure, using JSON with some specific keys, but some other just using simple string, and it's creating the chaos. And the third, the lack of context. A single error message means nothing without knowing what's else is happening in the system. Timeout may be fine, maybe it's happening frequently and the team know what's happening. But when it happens during checkout your e-commerce system on a Black Friday, it's a huge problem. So traditional tools don't give us the context. They just tell us error occurred, and it's up to us what we're gonna do. And we have, by the way, some classical approaches what people use. The first one, threshold-based rules. For example, when we have more than 100 errors in a minute, we gotta send an alert to the Slack or any other messenger to check it in our Grafana and stuff. It's simple and easy to implement, but it often creates alerts when nothing is truly wrong, and sometimes it misses subtle issues. For example, when developer is doing something important and he gotta change his context and check what's happening, it's getting problematic. The second, statistical methods, using moving averages, RIMA, z-scores to track deviations. These are useful for metrics like latency or throughput, but they don't understand logs in their semantic sense. And of course, the third one, basic ML models like isolation forest or clustering. These treat logs as data points and try to identify outliers. It's promising, but the models often break down when new types of logs appear, which is actually when we need them most, because we learn on the logs that we saw before. And why classical approaches fail? So, why do this method fail in the practice? They create too many false positives. If every little deviation triggers an alert, engineers stop paying attention. We had all the situation. The page just goes off, you look, and it's something harmless. They lack business context, as I said before, they gotta change their context, and have poor generalization. When the system encounters something new, classical models simply say, I don't know what is that, which either means they ignore it or they overreact. In short, this approach has flood us with noise while missing signals we really care about. And let's enter our embedded context agents. What is alternative? This is where embedded context really come in. Instead of positive and passive rules or static models, we embedded small intelligent components directly into observability pipeline. These agents they embedded, they live inside our system, analyzing logs in real time. The second one, contextual. They add business and system context to every log. And autonomous agents, they don't just look at the data, they act, alert, correlate, even fix small problems. In this case, we don't need to change the context of the developer. It's like moving from passive CCTV camera to an active security guard. And what does an agent do? So, step 1, it ingests logs in real time. Step 2, it enriches them with context. That means attaching metadata like which service, which deployment, which user, which region. And step 3, it analyzes these enriched logs using ML models, embeddings, or pattern recognition. And step 4, it acts. That might mean raising an alert, cluster an anomaly with previous incident, or even recommending an automated mitigation. It's not about just seeing data. It's about understanding it and taking the right next step. So, to make it more clear, let's use an analogy. For example, let's consider the mall where we have security guards. And in the mall, we have cameras that can observe everywhere. And it can check that people walking, shops opening, deliveries happening. That's useful, but it cannot be interpreted. So for that, we need some guy who will check everything and says what's happening. The guard doesn't just watch, they interpret. If someone is walking around the night in a closed mall, that's suspicious and he needs to react. But the same person walking on a Black Friday during a sale, nobody will pay attention. That's different context makes. Logs without agents are just raw video, but logs with agents are actionable insights. So let's talk a little bit about architecture. Initially, it will be something simple, but later we will deep dive. Regarding system architecture, how it looks like. Logs are ingested through all tools. It can be like FluentD, Logstash, or OpenTelemetry. There are a lot of solutions. So they go through contextual enrichment really. Agents add metadata like user ID, region, deployment details, and the next one is detection core. It can be the things that we discussed before, like classical approaches, but as well it can be ML models that analyze the sequence of logs and look for anomalies. And finally, the action layer. This is where alerts are raised, dashboards updated, in some cases automated response are triggered. It's a pipeline: ingest, enrich, analyze, and act. So in the next slide, we'll take a look at some primitive architecture. A lot of details are omitted, but some of them I will just consider. So let's imagine this pipeline. We have a few things. The architecture on the screen illustrates full end-to-end anomaly detection that system processes logs from multiple sources, enriches then individual information, applies machine learning, and finally routes the result into different destinations, and for visibility, action, and automation. The first one is, as I said before, log sources. The pipeline begins with the diverse resources. It can be some application logs regarding APIs like error, performance, transactions. As well, it can be some infrastructure logs like service, containers, cloud resources, and stuff. And the third thing is security thing. For example, when we have like SS attempts or audit trials or firewall events, and this represented the raw telemetry of the system. The second step, this is a log collector. It can be, for example, OpenTelemetry or FluentD and stuff. A log collector normalizes and ships the logs in real time. FluentD, for example, is responsible for collecting log files, parsing them, and applying lightweight transformations. It gives us when we have different formats to standardize. This ensures consistent structure and reduces noise before ingestion. The next step is message bus. Guys, that we have billions of logs every day, and we need to send them somehow without breaking the system. So the solution here can be some message bus. And in my opinion, the best one is Kafka. When we normalize the logs, then we push them to Kafka message bus. Kafka provides durable, scalable, high throughput streaming and decouples producers, log collectors from consumers' analysis engine. Enables replay and break pressure handling in case of downstream slowdowns. And the next step is embedded context agent. And the core sits the embedded context agent which orchestrates anomaly detection. It consists of 3 main layers. The first one, context enrichment ends. It can be like metadata, session info, user device context, and stuff. Helps models understand the story behind raw events. ML models isolation forest, detect outliers in high dimension data, and autoencoder, reconstruct normal patterns, flag deviations. But by the way, here may be used as well LLM-based models. It can be a little bit problematic, and later in this presentation I will explain why, but it provides semantic interpretation, anomaly reasoning, and correlation across logs. So, decision layer aggregates results from multiple models and applies rules for Ansible logic to classify anomalies, determine severity type and required response. Of course, the next step is backend services, where we need to orchestrate everything what we got in the previous layer. This component acts as a hub that routes classified anomalies into different destinations. It can be, for example, some dashboards like Grafana, Kibana, and stuff. And for example, want to understand that this is something urgent, we can notify by Slack and other messengers. As well, we need to keep this data somehow to use it again. And for this purpose, we have a databases like Postgres, Redis, and Elasticsearch and stuff. And for example, we can react on it at the moment. And for that, we can use like Kubernetes, auto mitigation. It triggers workflow, for example, scaling pods if load anomaly detected, or blocking an IP if instructions expected. Reduces MTTR, mean to recovery, to eliminate manual steps, or some other actions can be done on the programming language. And the last step is end users that get this information and can react. So this architecture provides resilient, scalable, and intelligent anomaly detection pipeline. Log collection and normalization ensure clean data. Kafka guarantees scalable streaming and reply, and embedded engine combine context, ML, and decisions. And output ensure both human visibility and automated remediation. It balances real-time detection with historical analysis and automated action, making it suitable for modern cloud-native and security-crucial environments. So, now let's take a look on detection core ML models. Detection core uses a combination of techniques. For example, autoencoders compress and reconstruct log patterns, flagging anything that doesn't fit. Isolation forests are great for identifying outliers. Logbird brings transformer-based embeddings and capturing the semantic meanings of logs. For example, we have as well DeepLog, uses LSTM to model sequence of log events. And by combining these, agents can handle both structured and unstructured logs, as well as a new pattern we've never seen before. Let's talk about multi-agent collaboration. Another important point, we don't rely on a simple agent to do everything. Instead, we use specialized agents. One focuses on network traffic, another on authentication pattern, another on performance metrics. Each of them act as a domain expert, but they can of course collaborate, where shared bus can be usually Kafka or a similar system. And together they can form an ecosystem of small specialized experts. For example, let's take a look on different agents. We have 3 main scenarios. The first one, for example, when we got some problem like 500 HTTP, when we did some order. The agent compares this with embeddings of known error classes, not much. It's a new, so it raises an anomaly flag. This gets an attention of DevOps before an error spreads. Without the agent, this error might just be buried in 1,000 of lines of logs and go unnoticed until customers complain. The next scenarios when we have, for example, suspicious logs. Like the authentication agent notices a spike in the login attempts from a region we don't really usually see the activity. We need to enrich metadata. For example, we see same API range, same data frame or time frame, and hundreds of late logins. It's not just technical error, it's potential attack. And by flagging it early, we can prevent account takeovers or data breaches. And the last scenario that I would consider is early performance warning. For example, sometimes the system metrics looks fine, like we don't have problem with RAM or CPU, and latency dashboards are green. But agents are noticing more and more logs, like slow query detected. Individually, it doesn't trigger an alert, but trend is obvious. The performance agent raises an anomaly alert, something is degrading. And the engineers can fix it before it becomes an outage. This is power of context and sequence-based detection. So let's take a look more about ML models. For example, DeepLog we got in 2017. It's a pioneer sequence-based anomaly detection, so it's a kind of recent technologies. Special log brought its 2021, applied to transform into logs. Log AI from Microsoft as an open source library for log parsing and anomaly detection. And as well, there is a DEN-free, for example, that helps build streaming logs templates. This is a building blocks, and agent combine them with domain-specific context. So, I didn't say something before, some about LLM, like ChatGPT, where it can be fit. This is actually a very good thing, for example, analyzing patterns and human-friendly language. That makes a great tool for engineers as well, day-to-day activity, but it has some limitations, unfortunately. For example, it's not real-time. Do you know how it's happening? We're doing some kind of request and we got to wait until we got the full request. It doesn't continuously monitor logs. It only works when you ask. And it's really hard to scale to millions of logs line per minute. You would spend a fortune trying to process all logs with this way. And finally, there are issues of privacy and cost. As guys, it costs a lot. Many logs contain sensitive data. Sending everything to a large model is not always safe and affordable. Of course, we can use like a local model, but still, it's not like a thing that can resolve everything. Now let's compare a little bit ChatGPT or LLM with ML agents that we discussed before. The reality is following. LLM and ML agents serve different purposes. For example, agents, they can be real-time, they can be scalable, they can be domain-specific, cheaper. But ChatGPT is a great explanation, of course, but still, it's not suitable for billions of requests. But the best thing we can use like a hybrid approach. I think this is the best setup. Agents continuously scan and detect anomalies in real time. They raise alerts, feed dashboards, and trigger automations when something serious is found. But when we're talking about LLM, it's helping engineers quickly understand what's happening, summarizing patterns, and suggesting possible root causes. I guess this approach will give us the best results. So, let's take a look a little bit benefits from embedded context agents. What are the benefits of using embedded context agents? Easy. They reduce noise by filtering out false positives. They operate in real time, giving you early detection, and extensible. You can add new engines for new domains. They integrate seamlessly with the DevOps workflows and CI/CD pipelines and bring intelligent closures of the data. Let's take a look at some challenges. But let's be honest, it's not all easy. There are challenges like training models, especially when it comes to the LLM-based. It can be expensive. Context must always be on up-to-date. New deployments, new services, configs. Explainability is hard. If an agent says there's an anomaly, engineer wants to know why. And agent coordination is tricky. Multiple agents might overlap or even conflict. This is areas where we still solve as a community. Let's take a look a bit at the future directions. First, RAG-full logs, combining retrieval of similar incidents with generative models. The second, self-healing systems, agents that don't just detect anomalies but also fix simple issues automatically. As I said before, for example, with Kubernetes that can kill the pods, but it's still not something huge. And the third, a federated anomaly detection, agent across clusters sharing their knowledge to improve detection globally. This is where the field is going, and it's a very exciting time to be working on it. Let's take a look a little bit at the use cases. For example, when we're talking about DevOps, for DevOps, agents are game-changing, imaging a deployment pipeline. As a new version rolls out, agents watch the logs in real time. If unusual errors spike beyond what expected during the rollout, they just automatically flag or even roll back the deployment. This reduces downtime and makes releases safer. And for example, it can be used as well for security. Agents provide another layer of defense. They monitor login pattern, user behavior, and errors. If they detect anomalies, say a sudden burst of failed logins or unusual API calls from a specific region, they raise an alert. By catching this early, you can prevent incidents before they escalate into breaches. So, let me conclude. Logs by themselves are just noise, but by the embedded context agents, logs are transformed into meaningful and actionable signals. These agents bring context, intelligence, and autonomy into log analysis. And for example, if we combine it with systems like ChatGPT or other LLM, they empower engineers to detect, understand, and respond to problems faster than ever before. And most likely, this is the future of platform engineering. Smarter, more proactive, more adaptive systems. So, thank you all for your attention.